In this video I will show you how you will work with circuits. Now this is not the most simple circuit. I have two resistors and one battery, but the process that I will show you here is going to be the same no matter how complicated your circuit is. So I'm gonna start by labeling the points. And you know what? To make my life easier, I'm not gonna make the two here. You will see why. I'm gonna say that point 2, well, I will use letters instead of numbers since I have R1 and R2 so that I don't get confused. This is A, this is point B, C, D, E, and then I'm going to F, and then from F back to A. So my loop will be from A, I go to B, C, D, E, F, and from F I'm going back to A. Alright, and I know around the loop that the potential difference will be 0. Now before I start doing this, I will make some assumptions here. It's not the most simple circuit, but also it's not the most complicated circuit. I do know how electrons move for this circuit. I know that electrons are going to leave the negative side of the battery, they're going to move clockwise, and they're going to go back to the battery from the positive side. So I do know that the electron current flows this way. Okay, this is the electron current because electrons will leave the negative side of the battery. Now, we saw before that unfortunately the convention is that we use the conventional current, and that is assumed to be the motion of the positive charges, which in most cases don't exist. It is the negative charges that move. In any case, if the electron current goes clockwise, that means that the conventional current is going to be counterclockwise. So this is the direction of the conventional current. Now what I'm going to draw around the circuit is the direction of the electric field inside the battery and in the resistors. So inside the battery, that's the positive side, that's the negative side. So I know that the electric field inside the battery will point to the right. And since I know that my electrons are going this way in the resistor, my electrons need to feel a force that points to the left. And because the force equals QE, if the force points to the left and I have a negative charge, the electric field will have to point to the right. So the electric field inside this resistor points to the right. And I do want to mention something that is useful. You will notice that the electric field and the conventional current are pointing in the same direction in the resistors, okay? In the resistors. Now, there are circuits for which you will not really know how your electrons move. In that case, if you have such a complicated circuit, it's okay to make an assumption, make a guess. Even if it is wrong, it will be fine. But you need to start your analysis of the circuit by drawing the electric fields and the directions of the electron current and the conventional current. You need these things before you can move on. All right. So delta V around the loop is 0. And I'm going to, as I said, I go from A to B. So VB minus VA plus VC minus VB plus VD minus VC plus VE minus VD plus VF minus VE. And I have one more term, so I'm going to write it here, plus what is left. From F I go to A, and that should be 0. Now here is what makes my life easy. If you remember, this is theory, and that means whenever I'm moving in ideal wires, the potential difference is going to be 0. From A to B, it's ideal wire, that goes to 0. From C to D, ideal wire, that goes to 0. From E to F, also ideal wire, so that goes to 0. Now, let's see what is left. From B to C, I go from B to C, the electric field points to the right. So I'm moving to the left, it goes to the right. When I'm moving opposite to the direction of the electric field, the potential increases. So that's a plus. From D to E, same idea, electric field points to the right, I move to the left, the potential needs to increase, so that is a plus. From F to A, I move in the same direction as the electric field, this needs to be a minus. Now, what will I include here? Well, from B to C, I'm moving across a resistor. So I'm going to use Ohm's law, I times R2. From D to E, I move across this resistor. So I'm going to do I times R1. And then from F to A, I'm moving across the battery. So it will be minus EMF equals 0. And your entire equation then becomes plus IR2 plus IR1 minus EMF equals 0. And this is what we get when we apply Kirchhoff's loop rule for this circuit. Now, if you happen to choose a loop where you don't go clockwise but you go counterclockwise, you would have gotten minus IR2 minus IR1 plus EMF equals 0. But at the end of the day, you get really the same equation. So what direction you choose to for your loop, it doesn't really make a difference. And I don't have any suggestions. Choose whatever you want. Make a choice. You do need to specify what your loop is. That's the important part. Now, let's say I give you that this is 3 volts. R1 is 1 ohm. R2 is 2 ohms. Then you're gonna find the current of 1 ampere. Okay, so if you want to solve, if what you're looking for is your current, the current in the circuit, you will get this. Okay, if this is 3, that's 1, that's 2, then you get the current of 1 ampere. Just a simple calculation. So this is how you can apply Kirchhoff's loop rule for this circuit. And I want to finish this by mentioning, when you have resistors connected like this, where the current that flows through them is the same, then we say that these resistors are connected in series. These two resistors, 1 and 2, are connected in series.